Hello, everyone. My name is Mihai Budiu, and I am presenting this work on behalf of my research collaborators. Our paper is titled DBSP, Automatic Incremental View Maintenance for Rich Query Languages. This paper is all about incremental computation. What does it mean to compute incrementally? It means that once you've computed something based on some input, I, if your input changes slightly, you'd like to avoid doing a full recomputation and ideally reuse what you've computed previously. And this ideally should perform work which is proportional to the size of the input and output change and not proportional to the size of the entire input. Okay, so what is in this paper? This paper's backbone is a very simple programming language called DBSP, inspired by signal processing. DBSP has only 4 operators. However, DBSP is rich enough that it enables us to express what incremental computations means. Moreover, given a program written in a DBSP language, we have an algorithm which generates automatically another program in the same language, which computes on changes only, incrementally. Moreover, we show that DBSP is rich enough to implement all important database queries. How powerful is DBSP? Well, it can express the entire relational algebra. It can compute on sets or multisets. It can handle fine nested relations as produced by group by statements or the inverse of it. And it can also handle aggregation. So essentially, you can express all of SQL in DBSP. But that's not all. You can express in DBSP recursive queries, which are very useful to do graph computations or stratified negation, which makes DBSP powerful enough to express the entire data lake language. You can also express streaming computations like joins or Windows aggregates, and even more. We show, in fact, that DBSP is Turing complete. And because we have this algorithm which incrementalizes any DBSP program, we get automatic incremental evaluation for any program expressing such a query. Okay, so the core ingredient of DBSP is a stream. Think of a stream as being an infinite vector indexed by time, where the elements are produced one after the other. In general, the values of a stream can have any type A, but we will make the requirement that values of type A have operations of plus, minus, and a 0. This might seem strange at the beginning, but if you think about it, if you want to talk about changes, you have to be able to add and subtract things. Now, when we compute on streams, we apply functions to streams. We call the functions applied to streams just stream operators to distinguish them from functions that compute on scalar values. Functions on streams can have one or multiple inputs, as shown in this picture. We show functions using boxes and streams using arrows in our diagrams. How can you create functions on streams? Well, there is one simple way. If you have a function that computes on scalar values, then you can convert it immediately into a function that computes on streams by applying the function to every element of a stream. This is called lifting. So the lifted function f, depicted by this up arrow, operates on streams if f operates on scalar values. Another way you can create streaming computations is by chaining together other streaming computations. You can compose them into more complex data flow graphs. This is just mathematical function composition. Finally, let me show you a very interesting stream operator, which we call delay, and denote by z to the power -1. This name comes from the digital signal processing literature. This is also a very simple operator. Given a stream, the delay operator produces a stream that is identical to the input, except is delayed by one time step. And it fills the first value with a 0. Okay, now that we have some basic building blocks, let's build some interesting streaming computations. For example, this circuit that is composed of 3 operators. What does it do? Well, it takes the input and it adds to the input negated and delayed by one time step. So if we write an equation for the output, the tth output will be the tth input minus the previous input. What does this do? It essentially computes the changes in an input stream. This is a very useful operator. We'll denote it by capital D. And essentially, O is the stream of changes of S. For example, if S is a stream of integers, the output of the D operator applied to the stream S will be the stream of changes to the input. Each element will be the difference between the current value and the previous one. Okay, here's another streaming operator. that is even simpler than the previous one, but is a little bizarre because it seems to use its own output as an input. What does this computation do? Well, the first output will be just the first input because it adds 0 to it. Remember that the delay operator produces 0 the first time. And the tth output will be the tth input to which we add the previous version of the output. So the t minus 1th output. If we try to solve this equation, we'll observe that the result is the tth output is the sum of all the previous inputs. It's also a very useful operator, which we call integration operator. We'll denote this by I. And this operator does exactly the inverse of the D operator on the previous slide. Given a stream of changes, this operator reconstitutes the original stream. In other words, D and I, when applied in sequence, cancel out. Now let me make a very bold claim. All databases that you are aware of are streaming databases. Let me explain. What is a database? It's a set of tables. Now, a database is modified through a sequence of transactions. Each transaction is a change applied to the database. Now, transactions are linearizable, so they form a sequence or a stream in our parlance. So let's denote by T the stream of transactions in the order they commit. Is depicted here at the bottom. So DB itself is not an immutable object. If we could think of DB as a stream of database snapshots depicted in this way. The kth snapshot of the database is the content of the database after we have applied the first k transactions. There is a very interesting relationship between these two streams, which is given by this equation. The database stream is the integral of the transaction stream. The database at time k is the result of applying all the transactions up to k, summing up their results. And this is not everything. Consider a view V defined by a query Q. Here's an example. Create view V as, and then followed by a SQL query. Given our sequence of database snapshots, what is a view? Well, a view is a virtual table whose content evolves as the database evolves. After we have applied k transactions, the view is the result of applying the query to the database snapshot at time k. So what does this mean? It means that the view is computed by the lifted query, where the query is a function of the database state. So the view is also a stream of view snapshots, where each view is computed by applying the query to the corresponding snapshot of the database. So what does it mean to maintain incrementally view V as defined by a query? This is the same picture as previously. Now remember, the database stream is defined by integrating the transaction stream. And we'll do one more adjustment to this figure. We'll add a differentiation operator after this diagram to compute the changes to the view V. And this ensemble of three operators, integration, followed by lifted query, followed by the differentiation or the delta operator, we call the incremental version of the query queue. This is our definition of the incremental view maintenance process. And we think it's a good definition because outputs can be small because the outputs are only changes to the view and not the view itself. And moreover, it's compositional. Both inputs and outputs in this picture are changes and not full objects. Now, this definition doesn't seem very useful because it does a lot of work, but we'll show that it has a very important property which comes from its compositionality. And the property is the chain rule. If you apply two queries in sequence and you want to incrementalize that composition, it's enough to incrementalize each query independently. So let me prove this to you. That proof is trivial, so I can do it right on the spot by pictures. This is the definition of the left-hand side of this equation. Remember, the incremental version of a composition of two queries is applying the integration operator, applying the queries, and then the differentiation operator. Now, remember that D and I cancel out, so we can insert a pair of those in the middle between the Q1 and Q2. And now we just use a function associativity to regroup this computation, and we obtain the right-hand side of this equation. Why is this equation so important? Because it tells us that we can take any query no matter how complex, as long as we know to incrementalize each component subquery, then we know how to incrementalize the full query itself. Well, there is a fly in the ointment, which is that these equations hold if the computations are done over commutative groups, but databases are not commutative groups, they compute over sets. Well, there is a trick that has been known for a very long time to solve this problem, which is to represent each table in database as a z-set, not just as a table. In a z-set, each row has an additional weight, and the weight shows how many times the row belongs to the table. Now, in z-sets, the weights can be both positive and negative. Now, this is very nice because a z-set can represent not only tables, and the database tables are z-sets where each weight is 1, but it can also represent changes to tables. For example, a positive weight indicates a row is added, and a negative weight indicates a row is removed. And moreover, it can represent multisets by having weights bigger than 1 attached to a row. And z-sets do form a commutative group, so they do solve the problem that we had. So we can actually use z-sets to implement all of SQL, essentially entire relational algebra and all the other operators required by SQL. And moreover, when we do this implementation, each primitive operator has an efficient incremental version, which does only work proportional to the size of the change. As a consequence, it means that we can implement any SQL query in an incremental fashion. So does this work? So it does work. And it works in several ways. First of all, we have verified the entire theory using a theorem prover. And second, we have implemented all this infrastructure as code as open source. We have a DBSP runtime, which is implemented in Rust, which provides all the database operators and their incremental versions, which is available under an MIT license. And if we have a full compiler that takes SQL and compiles it into incremental DBSP circuits. And moreover, we are putting our money where our mouth is. We have founded an early stage startup, which is developing this software stack. Okay, so my message to you is, don't think of streaming databases and incremental view maintenance as different objects. They are very tightly and inextricably linked as facets of the same complex structure. Thank you.